I'm Chris Connolly. All of the authors were with SRI International in Menlo Park, and I'm going to be talking about a method for implementing transcoding-resistant image steganography. It's not coming up here, so I'm going to have to refer to the screen here. So what are the motivations? Subverting state censorship. There's increasing popularity of social media, a lot of which involves images or video. Because of the volume of data, we're assuming that human inspection is impractical. So the adversary has to rely on automatic attacks. So we're trying to craft a scheme that is resistant to such attacks. But one of the things that social media does a lot is transcoding to reduce bandwidth. So images will often be resized, JPEG quality level will be reset, videos might be transcoded to a lower bit rate, those sorts of things. We want to be able to take care of that. And in addition, image video steganography is already embedded in certain systems, and we want to design a library that makes it very easy for people to try a different method. So our goals, to embed messages and images in video, to make the encoding robust over certain kinds of perturbations and transformations where it's not a perfect scheme, but it does seem to resist certain kinds of conversions that you'd find on Facebook, for example. And we want the encoding to be hard to determine through automatic means. So again, not perfect, but the certain properties of this particular embedding make it difficult for adversaries to get information about the embedded message. So this sort of points to one of the ways you can deal with this is using spatial frequency components in things like JPEG. JPEG compression is a lossy scheme that does its work in the frequency domain, and that's what we're going to target. So our approach is to construct a library, the JPEG embedding library. We call it libgel. Along with that library, we have some utilities, command line utilities for doing embedding and extraction. Two of the key items here in the middle are we use an adaptive and randomized use of frequency components, and we are exploiting lossy compression for error correction. So in other words, the quantization process that JPEG goes through actually helps correct errors that are are incurred during the transcoding and transmission process. So the library has a relatively small C API for integration with larger systems. So just to sort of go over what does JPEG actually do, on the bottom there you have two sort of diagrams that show you the compression and then the decompression processes in JPEG. Upon compression, what happens is the image is broken up into 8x8 blocks of pixels. Each 8x8 block is called an MCU. It is transformed, a discrete cosine transformation, turns that 64 dimensional vector into another 64 dimensional vector that's in the frequency domain. Then the highest frequencies are quantized, and that depends on the quality level that you set. So by adjusting the quality level, you can chop off more and more higher frequencies in the image, and that's where the loss is induced in the compression. And then a Huffman coding finally allows you to emit a JPEG packet or file. And then on the bottom there, you see the inverse process. So we do Huffman decode, then we dequantize to sort of reflate the frequency coefficients to their full scale values, and then do an inverse DCT to get the actual grayscale, color, pixels, whatever. So this process is done independently for luminance and then the chrominance. So you can do grayscale or color or both. Just to give you an idea of how the stabilization or the error correction happens when you're quantizing, on the left there you see sort of a dense distribution of frequency coefficients. The quantization will map those down to a much fewer set of values. So here, for example, we're going to divide by we're going to take the original frequency components you see on the left, divide by some factor that reduces every 3 components down to 1 value. And then when we reflate, when we do the decompression, you'll notice that we get sort of a coarse output. So those values, those 3 values that we started with, really decompress to only 1 value. So that's sort of, we're setting up a lattice, basically, such that if we're perturbing the image in the neighborhood of a point in that lattice, the decompression process will cause those points to coalesce on the lattice that gets sparser and sparser as we go down in quality. So the recipe for encoding here is we pick a JPEG quality, we decide how many chunks to encode per MCU, and we typically use 1 byte per MCU. So every 8 by 8 pixel neighborhood gets 1 byte of information embedded in it. And then we use 2 bits per frequency component. So we select 4 frequency components out of the 64 and stick 2 bits of information in the 4 components. We can also vary those frequency components using a pseudo-random number generator. That makes it a little more difficult to try and guess, for example, which components are being used. And then for each k-bit chunk of the message, really one byte chunk, we fetch the MCU, perform DCT plus quantization, and set the frequency components that we want, each 2-bit quantity, to each 2-bit chunk. And then dequant, inverse DCT, and then put the MCU back into the image. Actually, the JPEG library takes care of a lot of this for us. There's an API in libjpeg that allows you to deal strictly with the frequency coefficients, so it makes it very easy to kind of set the frequency components to the values you want. The choice of frequencies is dependent on the JPEG-based quality. So we're choosing frequency components that are still there, still present, but support, let's say, about 8 levels of quantization, somewhere in that range. So we have a fairly large selection of frequencies that we can still use, even down at quality 30. And gives you an example of the layout of frequency components for one MCU at quality 30. The entries that are labeled 0 are the frequency components that are completely blanked out at this quality level. So we pick frequency components that are roughly in that diagonal there where you see the 2s. And those are the ones that get heavily quantized but are still present. That alone is not enough to really prevent error from occurring. So we introduce error correction through Reed-Solomon coding. So basically, the idea is to break the message up into ECC blocks, and then each one of those blocks is encoded with a Reed-Solomon parity bytes. Let's see, what else do I want to say about that? So one of the other points here that to keep in mind is that the robustness of this method is dependent on the frequency components in the original image. In other words, the more texture there is, the high frequency texture there is in the original image, the more errors you're likely to see in the result as it's transcoded. So that's one of the motivations for going to something like ECC, to kind of help boost the performance. So we compared, did a number of comparisons with ECC, without ECC, using message length as a shared secret, or embedding the message length directly in the encoding and the embedding. And let's see, rather than go into the details, I'll just show you the results here. This is averaged over several images, and again, it's a range of frequency and textures in the image. So we wanted to try and get an idea of how well the method works under different circumstances and with different combinations of length as a shared secret and ECC. So the worst case is error with ECC enabled and length is embedded, and we think what's going on here, so those errors are very high. This is a percent bit error. So we measure the Hamming distance between the original message and the result that we got out after extraction. And the other thing I want to point out is that this is a transcoding test where we're starting at base quality, JPEG quality 30, and transcoding to some other quality here and then back to 30. So we want to see how the message survives that transcoding round trip. what's happening with the red is ECC with length embedding, and what we think is happening is that the length byte in each ECC packet is being corrupted. So that kind of suggests that maybe a dumb scheme for embedding length or encoding length. But the green is the best, seems to be the best case here, where length is a shared secret, but we're still using ECC. The errors go down quite a bit. But that's also the case for no length and no ECC. ECC makes it a little bit better, but it's not too dramatic in this case. The other thing that we wanted to try and counteract is the effect of rescaling. So rescaling often uses a filter. This is a Lanczos filter. Well, actually, there's a few different filters, but the Lanczos filter is pretty popular. So one of the things you have to do when you're rescaling and trying to recover the message is to do a sharpening operation, or some sort of a Laplacian. Our rescaling tests used ImageMagick, which uses the Lanczos filter and has a sharpen option that will tend to invert the filter. So with that in mind, we did a parameter survey here looking at robustness with respect to image rescaling. That's the absolute Hamming distance on the z-axis there, the vertical axis. The bottom axis there is the sharpening sigma, and then on the right there is the scale percentage. So we did the survey shrinking by up to 50%, and then expanding the image up to 150%. So that scale goes from 50% to 150%. And you'll see there's a large region there where we get little or no error in the recovery of the message. So that was a good sign that indicates that we are still able to survive rescaling, a wide range of rescaling. Here's another look at that with a finer sweep through for the scaling parameter. And you'll see that as we shrink the image, something we didn't see in the last plot because it was too coarse, but we see these bands of high error. So when we're shrinking, we have to be mindful of that. Another strategy might be to pre-expand the image before sending it in if you think that you're going to be subject to this kind of transformation. Let's see. So the other thing we wanted to look at were statistical attacks. How difficult would it be to determine that a message is being embedded in this image? And we tried a couple of different things. One was a Kolmogorov-Smirnov test, but it turns out that test doesn't do too well because we're using the most heavily quantized coefficients. So there are too few categories to actually come up with a robust comparison. We're also using all of the MCUs in the image, which makes it difficult for a self-calibrating attack to figure out that there's a message there, because the distribution is just, for those frequency components, just looks the same throughout the image. The other test that looks pretty good, actually, in many cases, is the Blockiness test, which is to look at, if you're modifying frequency components in the image, one thing you might want to do is to see whether there are spatial discontinuities across MCUs. So we implemented that test, which is described in one of Friedrich's papers. But that failed when we used a certain strategy, which is to use a quality 30 to embed and then transcode up to quality 90. We found that this is the kind of blockiness profile. So for the blockiness test to work, you're expecting a linear curve here that would allow you to predict the length in bytes of the estimated length in bytes is the prediction on the y-axis. The actual message length in bytes is on the x-axis, and what one wants to see for the blockiness test is a linear relationship there, but you see it completely fails. It doesn't allow you to say anything about the length of the message that's been embedded. There are a few issues. Length embedding, again, is fragile, so we may need to be smarter about that, or just use length as a shared secret. There are artifacts that show up in the images. You'll be able to see that, and so that's an issue that it will depend on the quality level, generally. And error is dependent on the frequency spectrum of the cover image. So the more texture the cover image has, the more likely you'll run into error in recovery. Another thing that we tried to do is look at how this works in Facebook if we were to try to embed a message in Facebook and then retrieve it later. We did find by experimenting that Facebook seems to want to use quality 71 in their transcoding. So we take an image, we embed using a command line utility wedge with length as a shared secret and a pseudorandom number generator seed also as a shared secret. Post the embedded image in Facebook, then retrieve the image from the Facebook page, transcode it back to the original quality, and then unwedge to retrieve the message. So here's two examples. The one on the left, you can see the artifacts at the top of the image there. It's a 640 by 480 image at quality 30, and there are no errors in that one. The right-hand side is a screenshot from a Facebook page. That's a view of Toronto from the CN Tower, 1024 by 1024, quality 65. There's about 5% error, a byte error. Modest success. We still have to figure out, experiment with this some more and see how well it goes. I just want to mention we've integrated this with Stegotorus and done some comparisons. These results show up in the paper. And I wanted to, while there's still time. Okay. Well, I have a few more slides. I don't want to, let me not shortchange this and just say that integrating with Stegotorus, the left-hand side there is I think the, to me, good sign that JPEG Steg doesn't seem to have much of an impact on the performance of Stegotorus. So that was a good thing to see. We can extrapolate this to look at video. So if we're doing this to specific image frames, we have a bandwidth issue. But if we expand now to video, we can embed a lot more information in a video, and that's obviously a popular thing to do on social media. So the easiest experiment that we could do was to look at motion JPEG video, which is really just a sequence of JPEG frames. So it's pretty easy to adapt what we're doing to that video format. So we took a video, we embedded blocks of the binary program GQ view into successive frames, and then just looked at what would it look like if you played this video back. So here we've got an example on the left, the cover video with nothing embedded. On the right, you see GQ view is embedded there, so you can see the artifacts. This is at quality 50. So you can, if you look carefully, you might see some stuff going on there, but it varies a lot, so it's not a static pattern. If I can go on, I can show you at quality 95 now. If you look on the right-hand side, it's much harder to see anything in there. So the question is, would an adversary, or even just a social media site, what quality level are they going to shoot for? The other thing, okay, enough of Rick. So beyond motion JPEG, what we really want to hit are codecs like MPEG, right? That's the real workhorse of video on the internet. Iframes are in JPEG and MPEG, excuse me, are very much like JPEG images. So they use the same kind of encoding, these DCT and Huffman. So there's hope that we can adapt what we're doing pretty easily to MPEG. One of the issues that MPEG has sort of been stuck with, or we've been stuck with in using MPEG, is the royalty issue, but it looks like Cisco has paid for an open source implementation of H.264, which is one of the codecs, which is an MPEG codec, that gives us hope that we can crack that open and start trying this out with MPEG. So summary, we want to take advantage of the popularity of social media, specifically images and video. We use the most heavily quantized frequency components to transmit information, and in so doing try to stabilize any perturbations that might occur. Quantization helps correct errors. It helps resist corruption due to transcoding and rescaling. This method is scalable to video as well. And then I also want to mention it's available on GitHub as a library, and we regularly build it on Linux and Mavericks. I'm not sure about Windows. And it's currently integrated with Stegotorus, but as a library, we hope that it can be plugged into anybody who wants to use it. That's it. Okay. I have not. I have not. We've done.
It's a benchmark that was created, I think, by Codecs for watermarking and image steganography. It does a bunch of transformations that you test to see the software available.
What was the name?
It's called Stirmark.
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 Right. We've seen it. We haven't tried that extensively. Yeah. We looked at watermarking schemes. Sorry, I have the backup slide. These are the sorts of things we did look at. Watermarking, so usually it's not a high bandwidth thing, but on the other hand, it's.
Well, yeah, this would be not a watermarking scheme, but a method to test the robustness of your scheme.
Okay, right. So it's a good idea. Yeah.
So I noticed it's interesting that you said the attack model is an automated bot, but not a human looking at it. So just naively speaking, when I was looking at the video, I couldn't really see what was going on. Why was it specified that a human looking at it might get something out?
I think we were just focused on an adversary model that, let's say, would because of the volume, we don't expect I mean, even if a human looks at this, can they tell that there's a message embedded in it? I don't know. But we didn't focus on that aspect of it. So we see artifacts. It's not steg as other approaches might be. Because when you look at it, you do see artifacts. But the question is, what are those artifacts? Are they really message, or are they just static? So for example, one use case for this might be with an IP webcam, where you're spoofing a webcam and embedding a message in that stream. That could easily be line noise, right? It's hard to tell.
I have a question.
Yeah.
Did you eyeball a frequency space, plot of the images you produced versus the, base case images? I'm
Right.
wondering if any kind of transform, you would see a big spike at a certain particular frequency, or
yes. So that's right. So that's one of the attacks. In fact, is to look at try to compare the distributions of cover images versus your steg image, and we were using the way we were using the KS test, the statistical test, was to compare neighboring frequency components. So we found that those distributions looked pretty similar, but again, that's going to depend on the image, the cover image that you use. So those distributions are arbitrary. So that's the thing.
And it also takes work to do that transformation.
Yeah.
To make that test.
Yeah, it can be expensive. Okay. Yeah.
I guess you've already got the slide. Can you just say some comparison with digital watermarking? Talk about that a little bit.
Yeah. So a lot of the watermarking schemes we saw were they used redundancy to kind of make sure that the watermark made it, right? So a lot of it was in the frequency domain, but the emphasis was on trying to make sure that watermark is preserved no matter what. And so they may use like a least significant bit kind of approach, but over a lot of different frequencies, or they may redundantly encode the watermark throughout all of the same watermark throughout I don't want to overstate this, is so using the frequency domain of the whole image as opposed to each MCU. I'm talking about MCUs for JPEG, but what some of these schemes do is they'll transform the whole image into the frequency domain, do the embedding, and then transform it back. So it's not dependent on JPEG, but it ensures a certain redundancy in the representation so that you can pull out. And a lot of the watermarks, too, are meant to be visually identifiable. So all you need is the appearance to come back, not specific bytes. So it's a long history there, so I'm probably underrepresenting what people do. But.